Agile Robot Navigation Through Hallucinated Learning and Sober Deployment by Xuesu Xiao, Bo Liu, and Peter Stone. One conundrum of learning safe motion planners is that in order to produce safe motions in obstacle-occupied spaces, a robot needs to first learn in those dangerous spaces without the ability of planning safe motions. Therefore, it either requires a good expert demonstration or exploration based on try and error, both of which become costly in highly constrained and therefore dangerous spaces. In our hallucinated learning and sober deployment, we address this problem by allowing the robot to safely explore in a completely open environment without any obstacles, and to hallucinate the obstacle configurations to the robot perception, where the motions executed in the open training environment are optimal. The blue and cyan rays represent the minimum and maximum range of a particular laser beam. We sample many times between these minimum and maximum values and generate a large amount of training data. These 5 videos show navigation performance in one example navigation environment from the 300 words in the Barn dataset. Hallucinated 1.0 fails many trials. The reason is learning from a dataset with varying speed and always hallucinating the most constrained spaces will cause ambiguity. The same most constrained seed space can map to different plans, which confuses the learner. Hallucinated 0.4 and Sober 0.4 both trained on a mostly constant 0.4 meter per second dataset without any ambiguity, achieve similar performance and are less sensitive to environment difficulty, especially Hallucinated 0.4, but it requires runtime hallucination and other components. Note, DWA has 1.0 meter per second max speed, while Hallucinated 0.4 and Sober 0.4 have up to 0.6 meter per second max speed, modulated from mostly 0.4 meter per second learned from the dataset. DWA has advantage in easy environments due to its fast speed, but in difficult ones, as the one shown in the video, Hallucinated 0.4 and Sober 0.4 are more stable. Also having 1.0 meter per second max speed, Sober 1.0 considers the varying linear velocity in the 1 meter per second dataset with our offset function, and achieves the best result, outperforming all other alternatives across the entire difficulty range. Detailed results in all 300 navigation environments of Barn dataset can be found in our paper. We also deployed the same set of local planners in a physical test course, 5 trials each. These 5 videos are example trials. The complicated obstacle course causes DWA to execute many recovery behaviors, such as rotating in place or backing up, and the robot takes a long average time with very large variance to finish the traversal. Hallucinated 0.4 and Sober 0.4 are both able to successfully navigate the robot through, with similar traversal times. But note that Hallucinated 0.4 requires a fine-resolution global path for hallucination during deployment and the turn-in-place module, while Sober 0.4 does not and only reacts to the real obstacles without any extra components. In this physical obstacle course, Hallucinated 1.0 fails every trial due to multiple collisions. Again, this is caused by the ambiguity in the training set's varying speed with constant most constrained hallucination. Our Sober 1.0 achieves the best performance both in terms of average time and standard deviation. This video shows synchronized first and third person views of Sober deployment in a natural cluttered environment. Note that before Sober deployment in all our simulated and physical trials, the robot has never seen a realistic obstacle during training in the completely open space. It learns to perform agile navigation through the hallucination technique described in our paper. That is, we derive the minimum unreachable set and then augment based on this minimum unreachable set with sampling. A large body of training data can then be generated and makes sure good generalization in unseen environments. Thank you for watching.